For those that might not be familiar, OptiSLang is a powerful tool designed for optimization problems, reduced order modeling, and process integration, which facilitates basically streamlined workflows containing different tools or softwares. And this can couple, of course, not only to Rocky, but also other Ansys products, Mechanical, Fluent, and so on. But speaking of, OptiSLang now has a guided workflow setup for the integration of the Rocky solver, which means we can now use this tool to perform sensitivity, optimization, robustness, and reevaluation analyses. I've put together two examples, which we'll look at today, but I've also got this interesting case study of a drilling process optimization problem where the analyst basically wanted to understand how the drill penetration and erosion on the drill bit will vary based on two parameters, the mud flow rate and the particle concentration. And then they wanted to find the optimal configuration, which will be conducive to the minimization of wear and the maximization of penetration, which they were able to essentially achieve this and satisfy their goals, and we'll soon see how something like this problem can be tackled with OptiSLang. So let's take a look at this example integration where I've just taken the same basic project, the lifting cylinder test, static angle of repose test, but this time, rather than just varying the rolling resistance, I've also considered the particle-to-particle static friction coefficient, and I've run a sensitivity analysis so that I can basically understand how the angle of repose will vary against the changes in these two particular coefficients. It's a slightly different model again with 10 millimeter particles compared to before, which used 16 millimeter particles. And we've been able to essentially generate a high quality response surface from 250 iterations or 250 solves, being able to capture the nonlinearity of this system. So as you can imagine, this is really great from a calibration standpoint, as we can build quite extensive knowledge bases without having to perform thousands of manual tests. But it's also, of course, applicable to design problems, as we saw in the previous case study, which used a sensitivity study to understand how that particle concentration and mud flow rate will impact and change the quantities or the outputs of interest. Now, one of the more interesting things that we can actually do from here is export the model from OptiSLang and make use of the Excel integration, which I'll just bring over to the screen here. So this is an example of the Excel integration. As I mentioned, we've exported that meta model out, which basically describes how the system will respond based on changes to various different parameters. In this case, we just had two parameters, friction coefficient and rolling resistance, and we essentially applied ranges to these parameters, lower bound to an upper bound, and essentially we've built that response surface to describe how the angle of repose will change. So to implement this in Excel, essentially I can run an infinite amount of design points to understand how the response of the system will change. So I could just add in more values on this list, make sure that the values I put in are within the bounds. So we could change this to 0.5, 0.7, 0.655, some random number that I'm typing, and do the same for friction coefficient. And you'll see that as I'm changing these values, the response or the outputs are changing as well. So essentially, down the line, when I'm calibrating or making some change to the design or operational conditions in a system, we can immediately predict what the response will be based on the meta model that we had already generated with OptiSLang. So similarly, rather than performing a sensitivity study, we can just go right ahead and set up an optimization problem, which is what I've done for this vibrating screen. Now here I've got two parameters that I'm interested in optimizing. the oscillation frequency, and the amplitude. And I'm interested, of course, in the screening efficiency. Obviously, we want to maximize this value. And of course, I'm also interested in the system power draw, which we want to minimize. At my baseline design, we're hitting a screening efficiency of only 74%. And the power draw, we'll use this more as a comparative value. So we do have a bit of time, so I'll jump into Rocky, and I'll showcase the sort of basic process of setting up or integrating the project into OptiSLang. But first, what we'll need to do is define the inputs and the outputs of the Rocky model, essentially. Now, this is a pre-solved model. It already has the inputs, the outputs, and all of the results. And you'll see them listed in the expressions/variables window, which again, you'll need to make sure that's activated in the tools or through the tools toolbar. Just make sure that's checked. And you'll see that I've created a number of inputs and outputs. Now, to create a new output, essentially all I need to do is take a curve or a property, some output that I'm interested in, and just drag and drop that into the window here. So take, for example, I could look at the particles, and maybe what I'll do is let's grab the velocity magnitude. I'll just drag that in there. So with a property, we need to convert that field of data essentially to a curve, to a singular value. So maybe we'll just take the average particle velocities, and let's just take the average over time of this curve. Select all and hit OK. You'll see it's thinking, taking a bit of time to report back that value, and you'll see that value reported back here. So that's great. We've created that output. On the input side, you'll see I've got frequency and amplitude defined as input variables. We can see where they're being used in the project under the expressions. So it's being used in this vibration motion frame for initial frequency and initial amplitude. So if we go ahead to the vibration motion, you'll see if I select that, it's just been defined by, rather than typing in 15 Hertz, it's been defined by myself typing in frequency and applying an initial value of 15 in this particular example. So that's great. We've set up the inputs and the outputs. Now what I need to do is just open OptiSLang and go through that guided workflow. Okay, I think the screen is being a little bit strange. There we go. Okay, so we'll go through, use the guided wizard. You'll see there's an Ansys Rocky among all these other guided workflows. Go ahead, hit Ansys Rocky, find the vibrating screen, but we'll need to make sure that the project that we're interested in integrating into Rocky or into OptiSLang is closed. So I'm not going to save that. Make sure that lock file disappears and point it to the Rocky file. I need to point it to this automatically generated export Rocky output script. It's just taking a second to think, bring up Rocky. It's going to clear the results, basically making a duplicate of the original parent Rocky project. So that'll take a second. Let it clear the results. That's going to close. And we'll go back to OptiSLang, and you'll see that it has created that automatic workflow for me. Now what I can do is just double click on the solver system, and you'll see that I've got my inputs that I've defined, the reference values from Rocky, and I could prescribe a range of values. So 0 to 25, 0 to 0.025, for example, hit apply, step through. Now here, for example, what I can do is define new variables, objectives, or apply some constraints on my inputs as well. But I'm going to jump back into the slides just in the interest of time, and let's take a look at the results, what I've got out of this example project. So the first thing is it's an optimization study, and I've used the tool in OptiSLang called the one-click optimization tool or method. This is basically a hybrid optimization strategy that can basically dynamically switch between different optimization algorithms, and actually run multiple algorithms simultaneously. So because of this, there's just basically one major setting that needs to be tuned, which is the maximum number of design points that it will run. So I set this to be a max of 80 design points, and for this particular model, it's solved in just about 12 hours, so just an overnight run to find the optimal design based on my parameters and the ranges that I prescribed for them. So it's been able to produce this optimal design, which I've just reported back the values. You can see the frequency has changed from, what was it before, 20 Hertz, now down to 18, and the amplitude at 9.4 millimeters. So what's been changed from the outputs? You'll see that the screening efficiency is now bumped up to 96% from 74%. These are just rounded to the nearest integer. Same thing with power draw. That's been reduced from 6,100 to 4,400, which represents roughly 28% reduction in power draw and a 22% increase in screening efficiency. And we can actually see the improvement in screening efficiency just over at these two images here, which are basically comparing the difference in the total collected mass of all the fines which passed through the overflow region. We can see, of course, in the optimized design, the mass is much smaller for the fines material than the baseline. So we had more fines passing through essentially the sieve. So what we can do with the optimization tool is generate this kind of plot. So this is a Pareto plot showing a Pareto front, which represents essentially the set of points which cannot be improved on for any objective without degrading or sacrificing at least one other objective. Effectively, what this is telling us, or what we can use and how we can interpret this data is, well, it's essentially a boundary which is defining almost the trade-offs between conflicting design objectives. So it might be a little bit difficult to see on screen, but the horizontal axis is representing the screening efficiency. So we want to maximize this. We want it on the right-hand side. And the vertical axis is representing the power draw, which we obviously want to minimize. And you can see what's interesting here is that, I mean, as you would expect, the minimum power draw is the one where there's no oscillations at all. Frequency and amplitude is 0. Power draw correspondingly is 0, but you'll see that that has the worst screening efficiency. So essentially, we can use this to make decisions because it helps us to visualize and understand the trade-offs between, of course, different design objectives. Now, the materials wizard is essentially a complete application which runs inside Rocky, and this can be used as a starting point for calibration. What's really nice about it is that it's essentially just a combination of the features that I've just outlined, so the Python API and the OptiSLang integration. The wizard uses a reduced order model generated with OptiSLang based on results of 3 material calibration tests. So the loose bulk density test, static angle of repose, and the dynamic angle of repose tests. An optimization solver is used to search the ROM to find appropriate candidates for the material input parameters based on, of course, your user inputs. So it's important to know that the current material wizard database was generated considering only spherical particles with the size distribution normally distributed with a mean of 25 mil and standard deviation of 2.5 mil. So it does not include data for other particle shapes or sizes, but more and more features and more data is being added to this materials wizard each release. But what's particularly useful about this is that users are basically able to effectively create their own material wizards, perform their own studies with OptiSLang, and export that meta model, that ROM, and use a Python script to basically access and run that within a little GUI as it's done in the materials wizard. So you can essentially create your own in-house materials library, database, or wizard using, of course, the Python API and OptiSLang integration.